What if I told you that your fully patched Windows machine is still vulnerable? Not to 0 days, not to cutting-edge exploits, but to techniques that have been known for over a decade. Techniques that have been reported to Microsoft and left unfixed, because fixing them would break how Windows works. I'm a red teamer. I break into corporate networks for a living, and I see them on almost every engagement. Banks, hospitals, retail, environments that are fully patched, compliant, loaded with security tools, and still vulnerable to the same techniques. So in this video, I'm going to show you what these attacks actually are, where they come from, and the reason they still exist. First up, search order hijacking. When a program runs, it often needs to load other components. BLL files, COM objects, system tools. When an application calls a DLL without specifying a full path, as shown here, Windows has to go find it. So it searches in order. The applications directory, then system32, then C/Windows, then the current working directory. If an attacker has write access to any of these directories that are searched before the legitimate DLL, they can place their own malicious DLL with the same name there, and Windows will load it into the application's process. And because it's running inside a trusted process, it can bypass controls like App Locker and even full antivirus. And in some cases, if that application is running as administrator, it can go even further, allowing a normal user to run code as administrator. And it depends on developers and users, you, not making misconfigurations. This doesn't just affect DLLs, it also affects the path environment variable. When you type something like git into a terminal, Windows searches for that executable through this list of directories in order. And in exactly the same way, if an attacker places a malicious executable in a directory that comes first in that list, it gets executed instead of the intended program. So here we have git running in PowerShell. Now, if we go over to system32 and copy calc into the C/mingw bin folder, rename it git.exe, and run git again from PowerShell, you see we get calc. And I have seen this in actual networks of extremely well-known companies, where for some reason C/temp was world writable, allowing us to hijack a service running as admin. There's another version of this too, which is probably more risky to the general PC user, COM hijacking. And this one doesn't require a misconfiguration. Here's how it works. Windows uses COM objects constantly in the background. Every time you open Explorer, every time an application loads, the right-click menu itself is a COM object. Hundreds of COM calls happening silently behind the scenes. When Windows resolves a COM object, it checks the user registry first, then the system registry. And because any user can write to the user registry, an attacker can register a fake COM object that sits in front of the legitimate one. Every time Windows or an application calls that COM object, it loads the malicious version instead. This is how malware runs on your system after it's been rebooted. No admin rights required, no obvious footprint. And because COM loading is completely normal Windows behaviour, antivirus struggles to detect your new malicious background process. Microsoft's position? Working as intended. The user registry is supposed to be user-writable. That's by design. Next, let's discuss a class of attacks that's been around for over 2 decades, and I still use it regularly as the first domino to fall for a complete domain compromise. It's called NTLM coercion, and the reason it works comes down to one core behaviour. Windows will automatically authenticate to network paths it's pointed at. The moment that happens, the attacker captures a hash that can be cracked or used directly in attacks like NTLM relay, which we'll come back to later in this video. Now, this isn't one technique, it's a whole family of them. Petit potem, print a bug, DFS coerce, Different methods, same result. Force a machine to authenticate, then capture the user's hash. This isn't limited to one protocol either. These attacks abuse how Windows automatically authenticates to remote resources over SMB, HTTP, WebDAV, and more. And over the years, multiple file types have been abused to trigger this behaviour. LNK files, SCF files, thing files, URL files, even icon paths. In some cases, you don't even need a click. If a file references a remote resource, like an icon hosted on an attacker-controlled server, simply opening a network share can cause Windows to automatically authenticate. No interaction required. Now, Microsoft's answer to this is things like SMB signing. And technically, they're right. SMB signing does mitigate NTLM relay attacks, but for many years it wasn't consistently enforced across environments. And even today, I still see large, well-known organisations running Windows Server 2000, 2003, 2008 without SMB signing enforced. And it only takes one system like that to cause a whole lot of damage. Because the real issue is this: Windows will authenticate outbound to almost anything it's pointed at, a behaviour that exists for compatibility but continues to be abused. So instead, Microsoft patches individual vectors. There's always another one, because the architecture stays the same. So we've talked about NTLM coercion, forcing a machine to authenticate to you, capturing the hash. But what do you actually do with it? This is where pass the hash and NTLM relay attacks come in. In NTLM authentication, Windows doesn't verify that you know the password. It verifies that you have the hash. Those are two very different things. Which means the moment I capture your hash, I can authenticate as you. For example, an NTLM relay attack allows me to intercept a live NTLM authentication exchange, or trick your machine into starting one using NTLM coercion. I relay the exchange to a system which accepts NTLM and doesn't have SMB signing enforced. Now I have access to that system as you. But relays like this have limits. That captured NTLM exchange is only valid for a short period of time. I can't save it, then replay on every machine on the network, and it won't give me long-term access. Pass the hash is different. I'm not borrowing a live authentication anymore. I have the actual NT hash. And once I have the actual NT hash, I don't need the plaintext password. I don't need to crack it. I don't need to reverse it. In NTLM, that hash is enough to generate fresh authentication responses to entirely new challenges. And once an attacker captures the NT hash, they can log into any server on the network you have permissions to access, which becomes a big problem for administrators. Microsoft's answer is to move to different technologies known as Kerberos. And in a perfect world, it would work. But in the networks I actually walk into, NTLM is everywhere. Legacy systems that can't support Kerberos, applications hard-coded to use NTLM, configurations that haven't been touched in 15 years. This is on almost every engagement I run. Every one. And the reason it still exists is the same reason everything in this video still exists. Compatibility. So it stays. And so does pass the hash. And this brings us to the final vulnerability. This brings everything you've heard in this video together and wraps it up in a nice little bow. The LSASS trust boundary problem. LSASS is the process Windows uses to handle authentication, and it holds in memory every credential that's been used on that machine, password hashes, Kerberos tickets, and sometimes even plaintext credentials from your browser, depending on the configuration. But here's the problem. Anyone with local administrator privileges can read LSASS and access the credentials and hashes on the machine. Microsoft says, that's fine, you're a local admin. On paper, that sounds reasonable. But if we take into consideration all the things we've seen so far in this video, it leaves a lot of scope to become a local admin. And once you do, every credential on that machine is exposed. In a domain environment, if an administrator logs into a machine, their domain admin hash is stored too. So reading LSASS gives you domain admin hashes and domain admin Kerberos tickets, resulting in complete network compromise from a single misconfigured server. Remember, we only need the hash, and the hashes of all users are stored in LSASS if the user has logged into that machine. So, let's finish up by looking at a very common chain of events which happens within corporate environments that run Windows. I guarantee when you hear of a company being completely compromised with a massive data leak, something like this has happened. An attacker lands on a network using compromised credentials, either through phishing or access purchased from an initial access broker. From there, they discover a piece of software running as admin that suffers from BLL search order hijacking. They place a BLL into the application directory, which is loaded by the admin process and creates a local user on the machine and adds the user into the local administrators group. Now they have persistent local admin access to the endpoint. The attacker dumps LSASS looking for reusable credentials, hashes, or privileged tokens. Initially, there is nothing useful there, so they force an admin interaction. They change the permissions on something like Outlook, which is used constantly. The user loses access, complains to IT, and within 20 minutes, somebody logs into the box to investigate. The attacker extracts admin hashes from LSASS and uses pass the hash to move laterally through the network. From there, they pivot into management infrastructure, servers, databases, backup systems, and eventually domain controllers. Microsoft has redesigned parts of this over the years, including moving Windows domains onto Kerberos with Active Directory. But the underlying issue never really went away. Whether it is hashes, tickets, tokens, delegation, cached credentials, or privileged sessions, there are still links in the chain that expose reusable identity material to an attacker who controls the endpoint. The technology changed, but the trust model did not. And that is why, decades later, Windows still remains a hacker's playground.